the answers of the homework. There are 2 exercises to do. After that, we'll talk about the World Wide Web. Then we will do some course evaluations. You will spend about 15 minutes with Professor Ross. He's going to ask you some questions about the course. And then we'll have a 15-minute break. And then we have a presentation after the break. So we'll take the attendance after the break and have a presentation. So about the homework, we had 2 exercises assigned last time. The first exercise was 27. Chapter 6. And that exercise talked about the TCP header, the transmission control protocol header, which is what we have on the screen. And the exercise was asking, can I see it?
I was not able to take the video.
I will come out very good with this light.
I think I need to play it off.
Yeah, I don't.
Oh, should I switch her?
Yeah.
So the transmission control protocol header has
Thank you.
an acknowledgement number which is 32 bits long. As you can see, the scale on the top is 32 bits. And we said that this acknowledgement number is used to specify the next sequence number that we expect to receive. So the transmission control protocol and the transport layer was handling connections and making sure that the packets are delivered in the correct order. And so we're tracking all the bits and pieces of each packet. And the acknowledgement number was used to specify the next sequence number that we expect. But also, as we can see here, there is one bit also called ACK, or acknowledgement. So the question is asking, why do we need this ACK bit? Keeping in mind that we already have a 32-bit acknowledgement field. Does the ACK bit add anything? Tell me what you think about this question. Yes?
Okay, well, you do need it. Right, you do need it because it helps the SIM bit tell the difference between the connection request and the connection acknowledgement. So.
Okay, excellent. So what the student is saying is that we need the ACK bit because it is used during the connection establishment, during the 3-way handshake, along with the SIM bit, the synchronization bit, to perform the 3-way handshake during connection establishment. Is it used for anything else? Guys, look at your homework. You just submitted that 15 minutes ago on Moodle.
I did mine Monday.
That's when it was due.
I did mine Monday.
You remember what you wrote?
Hey, that's what I wrote.
Did anyone else write anything other than that? Yes?
If it's set to 1, the acknowledgement number is valid. If it's set to 0, then it's invalid. The acknowledgement number is invalid and it will be ignored.
Excellent, very good. So what he's saying, this is it can be either 0 or 1. So if it is equal to 0, then the acknowledgement field is valid, which means that this segment contains an acknowledgement. I mean, can you say if it's set to 0 is valid?
No, invalid.
It's not. If it's set to 0, the acknowledgement field is not used. If it's set to 1, then acknowledgement field is valid. What does that mean? Is it possible to have a segment without any data? So this is the header and then the data follows. Is it possible to have a segment without data? So we said that segments without data are valid and they are used for acknowledgements only. So they are used to acknowledge that the data was received. In that case, the acknowledgement number is used. It is possible that the acknowledgement number is not used. That's when this act bit is set to 0. Okay, very good. And the other question we had was from chapter 7. It was about the domain name system. So we have seen that the domain name system is a hierarchical distributed system which maps names to IP addresses. So the question was, and we need these IP addresses to establish the TCP connection from the client to the server in order to, for clients to request web pages from the web servers. So we need IP address. If we browse to www.google.com, we can connect to Google and look at the Google web page if we have the IP address of Google. But because we can't remember IP addresses, we invented this schema to be able to assign names such as cisco.com or uscc.edu to IP addresses and servers so we can easier remember them. But TCP doesn't understand these things. TCP needs the IP address in order to establish connection. So the question was asking, which is question 3 from chapter 7. The question was asking, what if there was a hacker and the hacker brought down or crashed all the DNS servers in the world at the same time? Now, remember, this is a distributed system. The reason it's distributed is because if it was not, if all these things were stored in one place, then the hacker can hack that, and then we would have no access to DNS. We would be unable to obtain IP addresses. So that's why we have multiple DNS servers which handle a small zone of the DNS space. And if one of them goes down, it's fine because the rest of them still work. Just only a small portion would not be working. But this is asking, what if the hackers crashed all these things in the whole world? Would the internet still be usable? So, can anyone tell me what you wrote about this?
Yeah, it's very usable. It would be usable, it just won't be very fun to use. You'd have to know the IP address to the website. You can no longer just type in google.com to get anywhere. But you
Okay.
can still, in theory, use it. You just have
Yeah,
to
but,
know a whole bunch of IP addresses, which most
Yeah, like
administrators do.
the average person couldn't use it because they don't know what IP address is. They just know if you want to go to Google, you type in Google, but they don't know even know what an IPS or DNS is.
This is the same average person doesn't know what is an IP address. Yeah?
What's even worse is the length, how many characters you'd have to know, especially if you're like trying to go to a version 6 stuff. That's like 64 characters. Oh my gosh.
If we have
That's
the IP
people can't remember their 15 character
address,
password. Gosh, it'd be
now
awful.
we have seen 32-bit here in the TCP
Oh,
header,
yeah,
but
talk
the
about
version 6 is 128-bit.
That's
Can
even
any of
worse.
us remember 128-bit address?
Nope.
It's gonna be hexadecimal.
Nope.
I don't know, if you're using Chrome, it would still be usable because you could still like just use your browser bar to do a Google search for that specific website, and then you would just be using Google to track all your IPs, and you would just click on the link to go there. Like, it would still be pretty. A lot of people still do that, but then Google would be pretty much in charge of like finding the
Who does where? Who get the DNS from the DNS server?
Well, no, like Google would be able to like,
Yeah.
if you're searching for strings at that
Wait a
point.
minute, can you connect to Google
Did you
at
know?
all if you don't have their IP address
No.
of Google?
Well, in
Yeah.
Google Chrome, you can't type in things and it automatically goes to Google.
But it searches google.com.
Yeah, so it's
Can you do a search on Google through any code as any interface if you don't have the IP address of google.com? You need to connect to the Google server somehow, right? This is the IP address of Google here. Now I'm cheating here because I got the IP address because I contacted the DNS server through the command prompt and I got the IP address. So this
Google.
is Google now.
You put there the IP address.
In order to connect to Google or any other web server, we need the address. Because TCP understands IP addresses, he doesn't understand Google.com. Now the thing is, we can't. The question is asking, is the internet still usable? And the first student said yes, it's still usable if we know the IP address. The actual network is not down. Only the DNS server is down. The actual network is still working. And we can connect to web servers and anything else if we know their address. The thing is though that most people don't know the address because they don't know, they can't remember that number either, or they don't know what is an IP address and what it's used for. So for most users, the internet would be inaccessible and effectively would be unusable. It's very big. For next time, do the exercises 22 and 41 from chapter 7. And 41, and read the chapter 7. So today we continue with the chapter 7, which is about the application layer. if we remember our network model, is that coming up on the picture or should I turn on the light?
Yeah,
Huh?
it's coming.
If we remember our network model, the first layer was the physical layer. In the physical layer we have bits, which means we're transmitting rows, zeros and ones through the wire or through the air. In the data link layer, we were providing some structure to the row bits by giving them beginning and end through a special sequence of bits called the flag. And we're creating frames. In the third layer, only with these two layers, we could connect computers next to each other and have them exchange data. But they have to be connected from one end to the wire to the other. Now, in the next layer, we could connect computers through many intermediate hops or routers in the way, which means we could now route data or packets through long distances and through anywhere in the world through the network layer, which creates packets by prepending the IP header to them and assigning them IP addresses which effectively uniquely specify a physical location address of any machine which is part of the network. And so the network layer can locate them physically and route packets to them. So it does routing and IP and addressing. And the next layer, but it provides no guarantee that the packets will make it. So it only makes best effort attempt to deliver packets. If they don't make it, he doesn't do anything to fix that. Because they can be dropped by routers if there's congestion, or they can be just lost or whatever on the network. The next layer is the layer that provides us the guarantee that the packets will make it there, because it has the transmission control protocol, and it creates connections between the sender and the receiver and tracks all the pieces of the packet. It breaks it down into smaller pieces, or it combines small pieces into bigger chunks for transmission, and on the receiving side reassembles them back into the correct order, and it also handles congestions. And so in the last layer, the application layer is what we are talking about now. And this is the last layer, so we have pretty much studied the whole network, the way it's built through all the layers. And we said that in this layer, we don't have a particular unit, such as segment or packet or frame, because there are many applications which want to use the network that are sitting in this layer, and each one of these applications have their own units. Two applications that we have seen last time was the email. So the email is one application that needs to use the network. And the unit of the email is an email. The email has a header, length, it has a certain encoding, whether it contains other languages or whether it contains video, audio, or any emails. So it has its own data unit. The other application we have seen that uses network was the DNS. So the DNS has its own data units. Some other things that we mentioned that use the network was some of the applications on your cell phones. What is the most popular application on your cell phone that you use all the time?
Call.
Text message. So the text message is an application which needs to use the network, so it is located in this layer. especially the ones on the mobile devices. Pretty much, I mean, if you don't have service, on your cell phone, what would you use it for? Game? Is there anything else?
A paperweight?
MP3 player.
Or maybe calculator or something.
Play music.
Play music. So think most of the applications that we need, that we use on daily basis, need the network. Yeah, we have seen some of them. We'll continue now. Another application which needs to use the network and it's sitting in the network layer is called the World Wide Web. So the World Wide Web is an application which is sitting in the application layer and needs the network for what? What is it doing? It's a web of linked documents. So it's an application that links documents through hyperlinks. And that's all that it does. It's just there are a bunch of documents that are linked to other documents. And this is an application that's sitting in the application layer and needs to use the network. Now this application has grown tremendously in recent years, but the way it started was very interesting because until that time, all of the documents that we had were in linear fashion, similar to the way when you read newspapers. You read one line, next to the next line, next you go to the next article, or when you watch TV, you're watching whatever the TV is showing us. We can't change that. We can't change the order unless we switch to another channel. But other than that, we are bound to what TV is showing us. It's pretty much in linear fashion. In 1945, Vannevar Bush was the first person who came up with the idea of the way the human mind works. He said, we're thinking about something, and all of a sudden our mind jumps to another topic. And that other topic might make our mind jump to a third topic. These topics may be unrelated in any sequential fashion, but they would be rather like this. This is first topic, second topic, third topic, fourth topic, 6, 7, 8. It's like a graph. So he tried to model the way our mind works, and he said that documents should be allowed to be organized in this fashion. And much later, this proposal came to life. In Europe, in the European Center for Nuclear Research. A scientist called Tim Berners-Lee gave the initial proposal for a way of linked documents. And the purpose of this, linking these documents, was to link some scientific experiments in physics. He was a physicist. this proposal was published, and later on it was implemented. Just one year later, in 1990, is the first browser for the web. The first browser for the web called Mosaic. Now, until that time, I mean, these documents contained only text, and they were linked via the hyperlinks. So it's just text and links. And the first graphical browser that would display pictures and things other than text was this Mosaic. The next browser that came up was Netscape. And Netscape did huge profits. Later on, there was an agreement signed between the European Center for Nuclear Research and the Massachusetts Institute of Technology. The MIT agreed to run the United States part of the World Wide Web. And they created an official site called W3.org, which you can check out, that would list all the specifications and standards for the World Wide Web. In about between 2005 and 2001, commercial companies were allowed on that web. And when they were allowed, we had the dot-com boom era. That's when these companies started putting their businesses on the web, trying to create e-commerce sites and sell things through the web and just have their customers on there as well. So since then it has grown tremendously. So we said that we have links which will allow us to connect to other documents. How are these links implemented? How do they work? We have briefly seen this last time, but if we have a link then the way the links are implemented is they had to answer 3 questions in order to make these links work. The first question was, what is the page called? So what the page is called is part of the link, or this is called the Uniform Resource Locator, because it allows us to locate a resource in a unique way anywhere in the network. So the first thing is what the page is called, and this is part of the URL or the link. Now, as you can see, the page is called ITCS3166.html. So when the browser wants to browse to that web page, which is a client, he needs to tell which page he wants. the page is called IGCS3166, but also is located in a folder called AATZACHE. And it might be located in many other folders. These things have to be specified here and are considered part of the file name. So the whole path is the file name. The second question that had to be addressed is, where is the page located? Where is the page? Where do you think that this page is? This is our course website. Where do you think that this page is physically stored and sitting?
University server.
Yes, so it is at UNCC.edu web server. So this DNS allows us to specify a name of a server which is physically hosting the contents of these pages that we're browsing to. So this DNS allows us to specify a name, and then the DNS has to give us the IP address. Once we have the IP address, we can establish TCP connection, and we can connect to the network and request the page. Remember, the network layer by the IP address will identify where the UNCC is physically geographically located, and it will route our address to that location. Now, okay, we know which page we want, we know where it is. What else do we need to get the page?
Protocol.
So we need the protocol, because the protocol is what? The protocol, do you guys remember what is a protocol? We had this in a beautiful video in one of our presentations that was talking about how the boys talk to girls. Do you remember that? It explained what is a protocol.
There are rules that
Yeah, they have to follow certain rules or it's not going to work. Right? So we have the same situation here. The protocol specifies how the client is going to request the page from the server. So how is the client going to do that? So we have a client and server situation. So let's see what happens when we type this URL into the browser, or if we click this URL within another page. Either way, the same thing is going to happen. We have client and we have server. First thing it's going to do is determine the URL. Either we typed it in the browser directly, or we clicked it through the mouse. Once it determined the URL, it's going to do what next? What's the next step? That was in the call board.
go to DNS server.
Yes, and go to DNS to obtain IP address. If the DNS is alive, if it was hacked, it will reply with the IP address. When the browser browser has the IP address, it can connect through TCP to the server. The server is sitting there always. It's always waiting. There is a process called service or daemon, which means that it's running all the time in the background. And what it's doing is listening on port 80 for incoming TCP requests. When the request from the client arrives, then server says, okay, I received your request, I am alive, and I can establish connection with you. So the three-way handshake is followed to establish connection. Once a connection is established, the client can send an HTTP request to the server. The port 80 was the port that is used for HTTP. Now remember, we had many other ports, because HTTP is only for web pages, but we had seen last time we had other ports. Other protocols. For example, if the protocol is not HTTP but HTTPS, then we would use a different port here. It would be port 443. The HTTPS is for establishing secure HTTP. This is for bank accounts, like for encrypted connections. If we were to upload and download files, we would use the file transfer protocol, and we would use a different port, 21, and for the email it's port 23. So these ports were used in the TCP connection. These were like gates or doorways to connect to a particular machine. So HTTP request. So he's going to say, I'm using the hypertext transfer protocol, version 1.1 for example, and I'm issuing command to the server which says, get AATVACHE / IPCS3166.html. Now this get command is defined in the HTTP protocol. And there are other things that are defined. There are many commands that the client can issue to the server through this protocol. And these commands are in ASCII text, and they usually contain 4 letters. This is defined in the protocol. This is a procedure of the rules that the client has to follow in order to request web pages from the server. The server is also defined. The responses of the server are defined also in HTTP. And these responses are numerical codes. code for that is 200. So he will say 200 successful request. I have the page you want here, and I'm gonna send it to you. So he will send a bunch of code. He just sends code, HTML, head, body, text. It's a bunch of code that goes to the method to the client. And then the client is the web browser, which is a very silly application, and the only thing it does is to read the code, whether it's HTML or something else, and display it properly on the screen. So it's going to read here, okay, this text is in bold, I have this other text is in green color, I have a picture right here, and there is a link up there, and it will display that on the screen. And this is all that the browser is doing. So the browser is a pretty silly application. It can't do much other than read HTML code and display. If the browser has to do something more complicated than that, then it needs help. And this is in your homework for next time. So if the browser has to do something else, for example, display PDF file, or display YouTube video, or play some sounds, or whatever, then it needs a plugin to do that. Or if you can't get that plugin, it's going to open another process, which means another running application, to do that, whether to play video or sounds, or display PDF files or Word documents. Now, this server, is it always going to say success, everything's okay? Is it always going to say that? Or it can say something else? Remember, this is the official website that was created when the World Wide Web was established, that contains all of the specifications for the World Wide Web. So the web server either can say 200 okay, or it can issue other things, such as all of them are three-digit codes. The ones that start with 1 are just information. The ones that start with 2, such as 200, means success. Now, can the web server say something else? What if I said here, ITCS 9000? What's gonna happen? Instead of ITCS 3166, I said ITCS 9000. Is that going to display? I mean, if we give a course called 9000 and I'm teaching it, then probably I create a website for that. If not, then I'm going to get an error. The error in this case is the server saying 400 there is a problem with the client. All the codes that start with 400 indicate a client issue. In this case, the issue with the client is that the client is requesting page which doesn't exist. What other mistakes can the client make? Can you log in to Moodle? Can you log into another student's Moodle account? If you try to log in, you'll probably get an error, right? What kind of error do you think you're going to get? It'll say, forbidden. You don't have permission to access this resource. So it's your problem that you want to access this resource because you're not allowed to access this resource. This is client code. The codes that start with 500 is a server problem. I requested the web page 3166, but some hacker hacked the web server, and the web server is dead. What's gonna happen? I'm gonna get an error which says it's a server error. It's gonna say service unavailable, something like that. Service unavailable because the server's dead. Now, if I just requested this page 5 minutes ago, and again I'm requesting the same page from the same server, the server is gonna say, look, you already have this. I'm not gonna send it again because it hasn't changed since 5 minutes ago. And I don't want to cause overhead on the network by resending the same stuff to you which you already have. So just pull it up from your cache. Now, I've been talking about this browser being a silly application displaying HTML code. Now, if we want to do some more complex processing for these web pages, then we can write such a web page that runs on the server and it does some processing, and these are called dynamic pages. So when they do processing, these dynamic pages will generate a page that is different every time for each client. For example, when we log into Moodle to check our grades, let's say each student will have a different grade. Some processing has to be done on the server side to display to return unique page as a response to the client. Or if we check our bank account, we're going to get a unique page. This kind of processing is done on the server, and it oftentimes has to connect to a database to do that. If we have that, then we have a 3-tier situation. That we need to go through. We have client, then we have server processing logic, and then we have server connecting to database to obtain customer information or student information. So in essence, we have two types of web pages. The ones that run only on the client are usually HTML pages. They're static pages that don't change. They could be cascading style sheets, XML, or other things. And all the scripting languages, whatever we write in these scripts, these things run on the client side, like JavaScript or VBScript or something else. These scripts will usually do some client-side processing, such as when we fill in forms, our customer forms, when we order things online, or we fill in our information to log into Moodle or something else, they can check for errors before they send this off to the server. So these things are running on the client. The browser helper applications and plugins are also running on the client. The server-side processing is usually this Java server pages, active server pages, PHP, and other pages which would run code on the server and possibly connect to databases. So we distinguish two types of applications like that, of web applications. some other methods for HTTP. The methods that I listed here was get, post, and hello, but there are other methods. All of these methods the client can use as commands to issue commands to the web server when they connect to the web server. And as we said, the web server responds with numerical 3-digit code. If everything is okay, it will succeed, but it can display otherwise a variety of codes. Client code, server codes, or redirections. So, I would like to leave you for 10 or 15 minutes with Professor